Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The last pure mathematician. A peculiar form of laziness can sometimes be the signature of profound genius. Stanislaw Marcin Ulam, by his own cheerful admission, was a practitioner of this art. He possessed a mind that recoiled from laborious, lengthy computations, an intellect that preferred the elegant seismic shock of a single transformative idea over the patient accretion of detailed proofs. His genius resided in abstraction, in the formulation of questions that could reframe entire disciplines. This disposition, cultivated in the extraordinary intellectual ecosystem of interwar Poland, would make him one of the 20th century's most pivotal and, in some ways, most enigmatic figures. His story begins in a world of pure thought, a realm of infinities and logical structures, long before the terrible urgency of physics would claim him. His intellectual journey found its crucible in the city of Lviv, a vibrant multicultural center that was, in the 1920s and 30s, home to one of the most remarkable concentrations of mathematical talent the world has ever seen. The Louvre School of Mathematics was an institution without walls, its heart beating within the smoky, coffee-scented confines of the Scottish Café. Here, day after day, a coterie of brilliant minds would gather around marble-top tables, their conversations fueled by caffeine and an insatiable appetite for abstract problems. The towering figure of Stefan Banach presided, a mathematician of immense power who had almost single-handedly created the field of functional analysis. Alongside him was the clever and versatile Stanislaw Ulam, and among them the young, precocious Ulam, whose sharp insights quickly earned him a place in this inner circle. The atmosphere was electric with creative energy. Mathematics was performed live, as a collaborative, almost theatrical, act. Problems were posed, conjectures were scrawled directly onto the tables, and solutions, sometimes arriving after hours of intense debate, were celebrated as collective triumphs. The most significant of these problems were eventually recorded in a large notebook kept by the café's proprietor, a ledger that became legendary as the Scottish Book. To solve a problem from the book was a mark of supreme distinction, with prizes ranging from a bottle of wine to, in one famously difficult case, a live goose. This environment shaped Ulam's entire mathematical philosophy. He learned that the most valuable contribution was often the formulation of a truly deep question, a query that could unlock years of research for others. His supposed laziness was, in this context, a powerful intellectual filter, an instinct for identifying the essential core of a problem while leaving the subsequent more mechanical work of formalization to others. The mathematical world they inhabited was one still grappling with the foundational upheavals of the early 20th century. David Hilbert's grand program, which sought to place all of mathematics on a secure axiomatic footing, had set the agenda. Fields like set theory and topology were new frontiers, filled with strange and wondrous objects whose properties were still being charted. At the heart of many debates was George Cantor's theory of infinite sets and the controversial axiom of choice, a powerful principle that allowed for the construction of abstract objects whose existence was guaranteed without providing a method for their creation. The axiom led to profoundly counterintuitive results, like the Banach-Tarski paradox, a favorite topic of conversation at the Scottish Café, which demonstrated that a solid sphere could be decomposed into a finite number of pieces and reassembled into two spheres identical to the original. This result, a direct consequence of the axiom of choice, revealed the deep weirdness lurking within the foundations of mathematics. Within this landscape, Ulam made his first truly fundamental contributions. He became fascinated with measure theory, the branch of mathematics concerned with assigning a consistent notion of size, or length, or volume, to arbitrary sets of points. The Banach-Tarski paradox showed that our intuitive three-dimensional concept of volume fails for certain kinds of sets. Ulam's early work sought to understand precisely which sets were well-behaved enough to possess a meaningful measure. He posed a profound question: could a consistent measure be defined for all subsets of the real numbers? Working with Banach, he explored this problem, leading to deep results about the limitations of measure. His most lasting contribution from this period, however, lay in the highest echelons of set theory, in the study of what are now called large cardinals. These are hypothetical types of infinite numbers, infinities so vast that their mere existence would have cascading consequences for the structure of the entire mathematical universe. Their consistency with the standard axioms of set theory is a central question in modern logic. Ulam introduced the concept of a measurable cardinal, later refined to the Ulam measurable cardinal. Explaining this concept requires a step back into the abstract. A measure, as we have seen, assigns a size to subsets of a given set. Ulam imagined an infinite set, which we can call kappa, and asked if a two-valued measure could be defined on all of its subsets. This special measure would assign the value 1 to large subsets and 0 to small subsets, following a few logical rules. For example, the whole set kappa would be large, and any individual point would be small. The question was, could such a measure exist for an infinite cardinal kappa? The implications were staggering. Ulam was able to show that the smallest such cardinal, if it existed, would have to be enormous, far larger than any infinity typically encountered in mathematics. Its existence would resolve many open questions, including his own earlier queries about defining a measure on all subsets of the real numbers. The existence of a measurable cardinal is a hypothesis that goes beyond the standard Zermelo-Fraenkel axioms of set theory with the axiom of choice. It is a new axiom, a declaration of faith in a richer mathematical reality. Ulam's work provided the first glimpse into this new, higher realm of infinity. Today, the study of large cardinals is a central pillar of modern set theory, a direct lineage from the questions Ulam first formulated at a café table in Louvre. His method was one of conceptual breakthrough. He would see a connection, an analogy, a deep structural similarity where others saw disparate fields. He possessed an uncanny ability to translate problems from one area of mathematics to another, revealing their hidden unity. This intellectual style, born in the collaborative ferment of the Scottish Café, was perfectly suited to a world of pure ideas. The problems were abstract, the stakes were philosophical, and the currency was insight. This idyllic world of Polish mathematics, however, was living on borrowed time. The political storm gathering across Europe would soon sweep it all away, scattering its brilliant minds across the globe and forcing them to confront problems of a terrifyingly concrete and urgent nature. For Stanislaw Ulam, the journey westward to America was an escape from annihilation, but it was also an intellectual exile. The man who delighted in the abstract architecture of infinity would soon be asked to calculate the mechanics of destruction, a transition that would forever change both him and the course of history. The intellectual sanctuary of Louvre, with its spirited debates over coffee and cognac, was a world away from the sun-scorched mesas of New Mexico. For Stanislaw Ulam, the journey from one to the other was a passage through a looking-glass. The mathematician who had plumbed the depths of set theory and the abstract nature of infinity found himself in a secret city, Los Alamos, a place singularly devoted to a problem of terrifying physical immediacy. He arrived a geometer, a topologist, whose mind operated in realms of pure form. He would be compelled to become a physicist, and a reluctant one at that, applying his unique cognitive style to the most consequential engineering project in human history. The intellectual games of the Scottish Café had carried the stakes of reputation and insight. The calculations at Los Alamos carried the weight of global war and the future of civilization. At the heart of the Manhattan Project lay a question of extraordinary difficulty, one that resisted the formidable analytical machinery of the assembled physicists. The problem was one of neutron diffusion. To sustain a nuclear chain reaction, the neutrons released by a fissioning atom of uranium or plutonium must go on to strike other nuclei, releasing more neutrons in a cascade of exponential power. Some neutrons, however, would escape the fissile core, while others might be absorbed without inducing fission. Predicting the aggregate behavior of this swarming probabilistic cloud of particles was paramount. The fate of the entire project hinged on understanding whether a given mass and geometry of material would fizzle or detonate. The governing physics could be expressed in a complex integro-differential equation, a mathematical beast that accounted for the probabilities of neutron scattering, absorption, and fission at every point in space and at every possible energy. With the computational tools of the era, which consisted of mechanical calculators and rooms full of human staff, a direct solution was a practical impossibility. The project's theoretical division was facing a computational wall. Ulam's foundational contribution to breaking this impasse arose famously during a period of convalescence from a serious illness. With his mind temporarily freed from the daily pressures of the laboratory, he found himself playing solitaire. A simple question formed in his mind: what were the chances of a particular layout of cards leading to a successful game? He recognized that calculating these odds from first principles, by enumerating all possible sequences of moves, would be a combinatorial nightmare. A far more practical path to an answer appeared. He could simply play the game out, say 100 times, with that specific layout, and record the number of successful outcomes. The ratio of wins to total games would provide a remarkably good estimate of the true probability. This was the conceptual seed of what would become the Monte Carlo method. Ulam realized that the intractable problem of neutron diffusion could be approached in the same manner. Instead of attempting to solve the deterministic equation that described the entire population of neutrons, one could simulate the life stories of a representative sample. One could follow a single imaginary neutron from its birth in a fission event. At each interaction, a metaphorical roll of the dice, informed by the known probabilities of nuclear cross-sections, would determine its fate. Does it scatter? In which direction? Does it get absorbed? Does it induce another fission? By tracking the histories of several hundred such simulated neutrons and averaging their behavior, one could build a statistical portrait of the entire system's dynamics. One could determine, with increasing confidence, whether the population of neutrons would grow or shrink. He proposed this statistical sampling approach to John von Neumann, whose own genius lay in seeing the profound connections between logic, mathematics, and the nascent architecture of computation. Von Neumann immediately grasped the power of Ulam's idea, especially its suitability for the forthcoming electronic computers, which could perform the simple repetitive calculations of the simulation at inhuman speeds. It was von Neumann who formalized the method, refined its mathematical underpinnings, and gave it its evocative codename, a nod to the casino in Monaco where Ulam's uncle had gambled away family money. The Monte Carlo method was a paradigm shift. It substituted brute force, statistical simulation for elegant but unattainable analytical solutions. It was the perfect tool for a new age of problems, those characterized by immense complexity and inherent randomness. Ulam's mind, accustomed to the abstract structures of measure theory,
had supplied the key that unlocked a problem of applied physics, a solution whose descendants now power fields from financial modeling and drug discovery to computer graphics and climate science. With the end of the war and the dawn of the atomic age, a new, even more formidable challenge consumed the minds at Los Alamos: the thermonuclear bomb. Edward Teller, a brilliant and driven physicist, had championed the concept of a fusion weapon, the super, since the earliest days of the project. The initial design envisioned using the explosive shock wave from a primary atomic bomb to heat a cylinder of deuterium fuel to the stellar temperatures required for fusion. Yet, as the calculations grew more sophisticated, a fatal flaw emerged. Ulam, working with his associate Cornelius Everett, performed meticulous computations which confirmed a devastating conclusion. The fission primary would blow the fusion fuel apart long before it could reach ignition temperature. The super, as conceived, was a dud. For several years, the American hydrogen bomb program was at a complete standstill, a theoretical impossibility. Once again, Ulam's distinct mode of thinking, a blend of geometric intuition and physical insight, produced the conceptual breakthrough. He pondered the flow of energy from the primary atomic explosion. He understood that the vast majority of the initial energy is released as an intense, brilliant flash of radiation, primarily soft X-rays. This radiation pulse travels at the speed of light, far ahead of the lumbering, physical shockwave of exploding matter. This led to Ulam's pivotal idea: staging and radiation implosion. He conceived of a design where the primary fission bomb and the secondary fusion fuel were physically separate components within a single casing. The X-rays from the primary would flood the interior of the casing, and their energy would be absorbed by a material, a pusher, surrounding the secondary stage. This rapid heating would cause the pusher to ablate and expand violently, driving a powerful symmetrical shockwave inward. This implosion would crush the fusion fuel to immense densities and temperatures, creating the conditions for efficient thermonuclear burn. This was the secret. Compression was the key. By squeezing the fusion fuel before heating it, the reaction would become self-sustaining and vastly more powerful. Ulam took his concept to Teller. Teller, initially resistant, soon recognized its genius. He then contributed a crucial refinement, placing a fission spark plug, a rod of plutonium or uranium, at the center of the fusion fuel. The compression from the radiation implosion would cause this spark plug to go critical, providing an additional source of intense heat from within, ensuring a rapid and complete ignition of the surrounding fusion material. This synthesis of Ulam's staging and radiation implosion concept, with Teller's refinement, became the Teller-Ulam design, the architecture that made high-yield thermonuclear weapons possible. It was a moment where abstract ideas about radiation transport and hydrodynamics, products of a mind steeped in topology, were transformed into a blueprint for harnessing the power of a star. The reluctant physicist had thus shaped the twin pillars of the nuclear age. His statistical method made the first atomic bombs a calculable reality, and his geometric insight into energy flow unlocked the terrifying potential of the second generation of nuclear weapons. These were contributions born of wartime necessity and Cold War anxiety, the application of a pure mathematician's mind to the world's most violent problems. This work, however, also armed him with a new set of tools and a new perspective. The very computational power that his Monte Carlo method demanded would soon become a playground for his boundless curiosity, allowing him to turn his gaze from terrestrial destruction towards the cosmos, and even towards the fundamental questions of life itself. The intellectual energies unleashed at Los Alamos, once focused with singular intensity on the physics of implosion and fusion, began to radiate outwards into new and uncharted domains. For Stanislaw Ulam, The post-war landscape presented a universe of fresh problems, accessible for the first time through the nascent power of electronic computation. The very machines his Monte Carlo method had helped justify were becoming instruments of creative exploration. His mind, having grappled with the assembly of a star on Earth, now turned toward the challenge of traveling to the stars themselves, and to the equally profound mystery of how simple rules could give rise to the complexity of life. This was a period of breathtaking intellectual ambition, where the habits of thought cultivated in the crucible of the Manhattan Project were repurposed for grander, more constructive visions. One of the most formidable barriers to humanity's expansion into the cosmos was, and remains, a matter of fundamental physics elegantly captured in the Tsiolkovsky rocket equation. This formula dictates a cruel and exponential reality. For every unit of velocity gained, a spacecraft must expend a vast and ever-increasing multiple of that mass in propellant. Chemical rockets, with their relatively low energy density, are slaves to this tyranny. They carry their own reaction mass, and most of that mass is dedicated to carrying the fuel that will later be expelled. A journey to a neighboring planet becomes a colossal undertaking in logistics, while a voyage to another star system remains an object of pure fantasy. The problem was one of brute force efficiency. A new source of propulsion was needed, one that could provide immense thrust with minimal propellant mass. Ulam's solution, conceived in 1955 with colleagues like Cornelius Everett and Frederick der Hoffmann, was a concept of such audacious scale it still commands a mixture of awe and disbelief. It was called Project Orion. The idea bypassed the gentle, continuous push of a chemical engine in favor of a series of discrete, violent, and extraordinarily powerful impulses. The spacecraft would be propelled by a sequence of controlled atomic detonations. Small, specially designed nuclear charges, some yielding less than a kiloton, would be ejected from the rear of the vessel. Milliseconds later, they would detonate a safe distance away. The expanding plasma and radiation from the blast would strike a colossal, thick metal disc at the base of the ship, known as the pusher plate. This plate, connected to the crew and cargo sections by enormous, shock-absorbing pistons, would convert the explosive jolt into a powerful forward acceleration. The ship would ride a staccato of atomic heartbeats across the void. The physics was sound, a direct application of the principles Ulam understood so intimately. The energy density of nuclear fission is millions of times greater than that of chemical combustion. This translated into a specific impulse, a measure of rocket efficiency, so high it dwarfed anything achievable with conventional means. Calculations showed that an Orion-class vessel could reach Mars in a matter of weeks and journey to the moons of Saturn and back in a single year, a mission profile that remains formidable even for our modern probes. The project was pursued with considerable seriousness by General Atomics for nearly a decade, with engineers building functional models using conventional explosives to test the stability of the pusher plate system. Ultimately, Orion's fate was sealed by geopolitics. The Partial Test Ban Treaty of 1963, prohibiting nuclear explosions in the atmosphere and outer space, rendered the entire concept politically untenable. Yet, the vision endures. Project Orion remains the theoretical benchmark for high-performance space propulsion, a go-to design for studies on rapid interplanetary transit, and perhaps most compellingly, for the deflection of civilization-threatening asteroids, a task where its immense power offers a uniquely credible defense. While one part of Ulam's imagination was charting courses through the solar system, another was exploring an inner space of equal vastness, the landscape of complexity itself. This inquiry was spurred by his close friend and collaborator John von Neumann, who was wrestling with one of the deepest questions of biology and engineering. How could a machine create a perfect copy of itself? Von Neumann's initial thoughts involved a complex world of floating robotic components, a kinematic model that was conceptually unwieldy and difficult to formalize. He posed the problem to Ulam, whose instinct was always to distill a complex continuous problem into a simpler, discrete and more abstract form. Ulam suggested a radical simplification that would prove to be profoundly generative. He proposed abandoning the physical mechanics of robots and parts in favor of a purely logical two-dimensional universe. Imagine a vast checkerboard, or grid. Each square or cell on this grid could exist in one of a few simple states, for example, on or off. The state of every cell would then evolve in discrete time steps, according to a simple deterministic rule based on the states of its immediate neighbors. This conceptual framework was the birth of the cellular automaton. It transformed von Neumann's problem from one of mechanical engineering into one of pure information and logic. Using this structure, von Neumann was able to design his famous 29-state universal constructor, a pattern on a grid that, when its rules were applied, would build a copy of itself and its own instruction set, a stunning demonstration of machine self-replication. This mode of thinking, exploring the global consequences of local rules, became a hallmark of Ulam's later work. Its power was revealed to him once more in a moment of pure serendipity. As the story goes, he was enduring a particularly tedious lecture and began to doodle on a sheet of graph paper to pass the time. He wrote the number 1 in the center. He then wrote 2 to its right, 3 above that, 4 to the left, 5 below, and continued outwards, creating a rectangular spiral of the integers. Out of idle curiosity, he began to circle all the prime numbers. What he saw was astonishing. The primes, which appear to be distributed without a clear pattern along the number line, showed a striking and inexplicable tendency to align along certain diagonal lines within his spiral. A simple, almost childlike arrangement had unveiled a hidden deep structure in the fundamental building blocks of arithmetic. This Ulam spiral was a perfect embodiment of his scientific philosophy that profound and beautiful patterns often emerge from the simplest of constructions, and that the act of playful visualization can be a powerful engine of discovery. The legacies of these post-war visions are immense. Cellular automata have become a foundational tool in the modern study of complex systems. They provide models for everything from the growth of crystals and the dynamics of fluids to the spread of epidemics and the flocking of birds. They are the bedrock of the field of artificial life and a constant source of inspiration for generative artists. The Ulam spiral, while its properties are still without a complete theoretical explanation, continues to intrigue number theorists, a beautiful visual mystery whispering of a deeper order in the primes. Both Orion and the automaton were products of a mind that saw the universe in terms of discrete interactions and emergent phenomena, a perspective perfectly suited to the new age of digital computation. These explorations were more than isolated achievements. They were rehearsals for a new kind of science, one where the computer served as a laboratory for the imagination, an instrument for generating intuition in realms where human senses and classical equations fell short. This experimental computational approach to fundamental questions would soon lead Ulam to his most startling discovery, one that would challenge the very foundations of statistical physics. The intellectual atmosphere of mid-century physics was saturated with a powerful and elegant assumption, a cornerstone of statistical mechanics known as the ergodic hypothesis. This principle held that for a sufficiently complex system with many interacting parts, energy would inevitably and rapidly diffuse throughout all possible modes of motion. Picture a vibrating string, composed of many linked particles. If you pluck one particle, giving it energy, ergodicity predicts that this energy will quickly bleed into its neighbors, and then their neighbors, until the entire system is a chaotic, uniform sea of thermal vibration. The system would achieve thermalization, its memory of the initial state completely erased. This was the accepted wisdom, a theoretical truth so foundational it was rarely questioned. For Stanislaw Ulam, whose mind was now attuned to the surprising behaviors of discrete, interacting systems, such a universally accepted truth represented an irresistible target for computational inquiry. He saw an opportunity to use the MANIAC computer at Los Alamos, the machine that had helped simulate thermonuclear reactions, as a new kind of microscope. He proposed an experiment of unprecedented nature to his collaborators, the physicist Enrico Fermi and the programmer Mary Tingu, later joined by John Pastor. They would model an idealized one-dimensional string as a chain of 64 particles connected by springs. Crucially, they added a small non-linear term to the force between the particles, a tiny deviation from the perfect solvable harmony of Hooke's law. This non-linearity was the essential ingredient, the theoretical gateway through which the system was supposed to march inexorably toward ergodic chaos. The experiment was designed to watch thermalization happen. Fermi, a titan of both theoretical and experimental physics, reportedly bet that the system would thermalize after a few thousand computational cycles. The MANIAC was set to work, calculating the intricate dance of these 64 particles over time. The initial state was simple. All the energy was placed into the lowest frequency mode of vibration, a smooth, single sine wave. The team watched the output, expecting to see this clean wave rapidly decay as its energy cascaded into higher, more chaotic frequencies. At first, the simulation behaved as expected. Energy began to seep from the first mode into the second, then the third. The wave grew more complex, and then something utterly astonishing occurred. The process reversed itself. The energy that had spread into the higher modes began to flow back, coalescing with uncanny precision into the original pure sine wave. The system, far from forgetting its initial state, returned to it almost perfectly. This became known as the Fermi-Pastor-Ulam-Singu recurrence. The result was a profound shock. It flew in the face of decades of physical intuition. The system was complex and non-linear, fulfilling all the prerequisites for statistical chaos, yet it exhibited a behavior closer to a perfectly ordered periodic clock. It was as if one had poured cream into coffee and watched it, after a brief moment of mixing, spontaneously unmix and gather back into a single, pristine dollop. The discovery was so counterintuitive that the team initially suspected a bug in the code or a flaw in the computer. Repeated runs confirmed the phenomenon. The small non-linear forces which were supposed to be the agents of chaos were instead orchestrating a hidden long-term order. This single experiment, born from Ulam's suggestion to probe a fundamental assumption, marked a watershed moment. It was the birth of computational physics, demonstrating that the computer could serve as a generative instrument for discovering entirely new physical phenomena. Furthermore, it planted the seed for what would blossom decades later into the rich and sprawling field of chaos theory. The FPUT problem revealed that the transition from order to chaos was a landscape of immense subtlety, filled with unexpected islands of stability and recurrence. Examining the full arc of his career reveals a contribution that permeates modern science more deeply than any single theorem or device. He bequeathed to his successors a powerful new paradigm of inquiry. The Monte Carlo method, the cellular automaton, the computational exploration of thermonuclear dynamics, and the FPUT experiment all share a common philosophical core. They represent a way of doing science that embraces complexity, uncertainty, and emergence. Ulam's genius lay in his ability to identify problems where pure analytical mathematics reached its limits, and where computational simulation could provide a new form of insight. He understood, perhaps earlier and more profoundly than any of his contemporaries, that the computer was an intuition amplifier. It was a tool for asking what if on a scale previously unimaginable, allowing the scientist to observe the behavior of complex systems that defied closed-form solutions. This approach represented a fundamental shift in the relationship between the mathematician and the physical world. The classical tradition from Newton to Einstein sought universal laws expressed in the elegant language of differential equations. Ulam pioneered a complementary path. His work demonstrated that one could gain profound understanding by building systems from the bottom up, defining simple local rules, and then observing the complex, often surprising, global behavior that emerged. This is the logic of the cellular automaton and the spirit of the Monte Carlo method. It is a way of thinking that is native to the digital age, a perspective that sees phenomena as computational processes. His influence, therefore, is written into the very methodology of modern research across countless fields. When a climate scientist runs a massive simulation to understand atmospheric dynamics, they are working within the Ulam paradigm. When a biologist models the folding of a protein by simulating the interactions of thousands of atoms, they are his intellectual heir. When an economist uses agent-based models to study market crashes, or a neuroscientist simulates a neural network, they are employing the conceptual tools he helped to forge. He was a bridge figure, a vital link connecting the abstract world of Polish set theory with the pragmatic, world-altering demands of the Manhattan Project and the nascent possibilities of the digital computer. Stanislaw Ulam's ultimate legacy is the profound understanding that the most creative act in science is often the formulation of a fruitful problem. He was a connoisseur of questions, a master problem poser who saw the entire universe as a collection of fascinating puzzles waiting to be explored. His autobiography, Adventures of a Mathematician, reveals a mind constantly in motion, flitting between abstract measure theory, the biology of cell division, and the trajectories of stars, always searching for the simple underlying question that could unlock a new domain of understanding. He showed that true progress comes from the courage to challenge foundational assumptions, the imagination to invent new methods of inquiry, and the wisdom to recognize a surprising result for what it is, a whisper from the universe, revealing a deeper and more intricate reality than we had ever conceived. He taught science a new language, a way of conversing with complexity itself, and in doing so, he helped define what it means to be a scientist in our computational world.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.